So it is known as resonance. It is known as resonance. So basically, so when a voltage applied to any electrical network containing resistance, inductance, and capacitance is in phase with the resulting current, right? The circuit is said to be a resonant, and the phenomena is known as resonance, right? So here the concept is very simple. So let us assume that we have a resistance, an inductance, and a capacitance is there, right? So a voltage is applied, and so this is the current. So we have this R, this is L, and so this is C, right? So we have three elements are there. So one is resistance, inductance, and capacitance are there, right? The thing is that, so when this voltage is in phase with the current, when this voltage or when this resultant current is in phase with the voltage, so then the circuit is said to be in resonant, or this phenomena is known as resonance. So when it will be in phase with this voltage in phase with current, so when this will happen,
Only resistance is
Only resistive circuit.
only resistive circuit, right? But you have two elements are there. So we have two elements are there, right? So this can be written as J into XL, right? So this can be written as minus J into XC. So when this circuit will be only resistive,
XL equals to
XL
XC.
minus
XL
XC.
equals
XL
to
equal
XC,
to
sir.
XC. So this circuit is only resistive, right? So now what will happen? So if this is the case, if XL equal to X is this is the case, the circuit is having some Z, right? What is the Z for this circuit?
R.
So it will be R square plus XL minus XC square, right?
RIS.
So at resonance, if XL equal to XC, so what? So this is the minimum impedance, and this will be the maximum current, so that can flow through the circuit because the impedance is minimum. So eventually, so the therefore the current will be maximum, right?
सर
Yes.
आप फिर से बोल सकते हो क्या? आवाज नहीं आ रही थी आपके बीच में.
It's okay. So let us assume that we have a circuit like which is having three elements, say resistor, inductor, and capacitor, so which is energized with some AC source, right? So now if we assume that if XL equal to XC, if XL equal to XC, so this Z or the impedance of the circuit so will become equal to so this resistant itself. So under this condition, so this will be the minimum impedance that is possible, right? And the current, so which is V by R, so that will be the maximum current. And this circuit is known as resonant circuit, and this entire phenomena is known as resonance. So under resonance, the voltage applied to the circuit and the resultant current, so both are in phase. In other words, effectively the power factor is how much? The power factor is 1, right? The power factor is unity or power factor is 1, and the circuit is looks like a purely resistive circuit. The circuit look like a pure resistive circuit.
So it's XL minus XC or XC minus XL, sir?
Yes.
So is it
So both are
XC?
same, right? If it is square, so obviously both are same. So XL minus XC or XC minus C, so both are same, right?
So we don't need to consider if it's lagging or leading or anything, right? Just
If it is both are equal, right? That's the different story.
yes, okay, fine.
Okay, so based on that, how you will decide the power factor, that is different thing, right? Okay. So now under which condition, so this XL and XC, so will be equal. You know what is XL? J into, what is XL? Omega L, right?
Omega L.
So which is equal to J into 2 pi FL. So this is equal to minus J into how much this is?
1 upon omega c.
1 upon omega
Omega
C.
c.
So 1 upon 2 pi F C.
C.
So what you understand that, so this is vary with the frequency. So this is also vary with frequency. Agree?
Yes, sir.
So let's assume that the source, we have source is there. So assume that its magnitude is fixed one, but the frequency is variable. But frequency is variable. Agree? Understood? The frequency is variable. So you're starting from, right? So here somewhere you're starting from 0, right? Somewhere you have, for example, 10,000 is there, H. So you're changing its value, or we are rotating that, so or we are changing the frequency. At some particular frequency, right? At particular frequency, so we can observe that, so this XL and XC value, so both will be same. Right? In other words, you can put this in a graph. It will be something like this. So this is the frequency. So one side you have frequency, so which is changing from 0, right? So how this J omega L look like? So this is assume that, so this is JXL. So obviously this is J into minus XC. So how this J omega L look like? So how it look like if the frequency is changing?
Linear change.
So how it will change? So it will change something like this, right? Agree?
Yes, sir. Straight.
Agree? So this is XL equal, this is 2 pi F into L. Agree? So next, so how this will change?
Hyperbolic.
Hyperbolic, right? Is it in the upper side or on the downside?
Downside.
Downside, right? Because it is J ray. So how it will exactly look like? It will be something like this, right?
Yeah.
Agree?
Yes, sir.
Right. So maybe at some particular frequency, for example, this is the, so this is the frequency. Roughly, right? So this is the frequency. So this value and this value, so this one and this one, so both are same. Okay. At some particular frequency, say for example this frequency, so that is resonant frequency. Say it is FR. So this is equal to 2 pi FR into L. So which is equal to, right? So which is equal to 1 by 2 pi FR into C. So that means XL equal to XC. Understood? So if you're drawing a plot with respect to the frequency, right, at some particular frequency, so this XL value is equal to XC. So that frequency is known as resonant frequency. That frequency is known as resonant frequency. So we
Okay,
have
sir.
this relation, yes?
So from the diagram, could you please explain again how XL and XL and XC are same? So because we are taking one point now, we could take any other point also, it will be the same only.
So why it is same? This magnitude is supposed to same, right? So this one will show me only at 1 point only.
So could you please explain again, sir? I'm kind of confused. We took magnitude and
Explain here.
no, sir. I'm asking like we took magnitude as unity, right? And frequency is only one changing. So, and sir, we are plotting in two different scales over. So I'm not able to understand.
Why two different scales? Only one scale you have. CK. Right? So this is varying like this, right? This curve is varying like this, agree? And this is occurring like this, right?
Yes,
Understood?
sir. Yes,
Okay.
sir. That understand.
So at certain point, right? At certain point, right? So this is, maybe it is XL, right? Some value. And this is also some value. This is XC. At certain point, so we may, right, if you change its frequency, at certain point, this XL may be equal to XC, right?
Yes, sir.
Okay. So that is the
Okay.
frequency, right? So if you assume that the frequency is FR, right? So here the corresponding, this value is here. So this is its corresponding value. So this value, so this is XC, right? And similar, this is its corresponding value. So this is
And that-
XL.
Yeah.
So this is XC at resonance, and this is XC at XL at resonance, right?
Yeah. Yeah. Fine, sir. Got it. Got it.
Right.
So
So at
basically,
resonance, you had 2 pi FR into L, so which is equal to 1 by 2 pi FR into C.
so this is
So
not
if-
any ideal condition, right, sir?
Hmm?
This is not any ideal condition, right? Because it's an achievable condition, right? Like when XL is going, XL and
This is
XC are
obviously it is possible, right?
okay. Fine. Sir.
It's
Okay.
not an ideal thing. So it is a practical thing only. So what is
Okay.
FR? So from this, what is FR?
FR is R square. 1 second. Sir.
1 by 2 pi root
1 by
2 pi
2 pi square
to
root.
del C.
Root LC.
Root LC, sir.
Okay. So this is known as resonant frequency. So this is known as resonant frequency. In other words, the meaning is at which the inductive reactance is equal to the capacitive reactance in a series RLC circuit. So that is known as resonant frequency. The inductive reactance is equal to the capacitive reactance. So that is known as resonant frequency. Right? So that is known as resonant frequency FR. So it's 1 by 2 pi omega r. It is if it is an angular form, omega r equal to 2 pi into FR, radians per second. If you know the L and C values, so you can find out the resonant frequency, so which is known as 1 by 2 pi square root LC. If these elements are in series, RLC are in series, so this is particularly known as series resonance. So this is particularly known as series resonance. Similarly, we have parallel resonance, so that we'll discuss in later classes. So at resonance, or in particularly at series resonance, the impedance of the circuit is minimum, right? The impedance of the circuit is minimum, and the resultant current is maximum. And the resultant current is maximum. At series resonance, the resultant current is maximum and the resultant impedance is minimum. Clear?
Yes, sir.
Okay. So now the question is from 0, right? some frequency is there, right? For example, it is operating. So 0 less than F less than FR, right? So what kind of circuit it is? Is it an inductive circuit or a capacitive circuit? What is the circuit behavior from 0 to FR?
Sir, capacitive?
Yeah, good. So why it is capacitive from 0 to FR? So this is the range, right? So 0 to FR. So 0 to FR means, so this range, so during this range, if you observe that the capacitive reactance will be more when compared to the inductive. So this is more, right? So when compared to this one, so therefore the circuit behaves as a capacitive. So the circuit behaves as a capacitive. At F equal to FR, the circuit behaves as a resistive. So that at resonant frequency, it is acts as a pure resistive, right? From F greater than FR, if F greater than FR,
Inductive circuit.
Inductive
circuit
circuit.
is inductive. So circuit is inductive. Okay. So if you draw a curve, right? If you draw a curve for the impedance, so impedance we have, so this is impedance, right? So impedance, so Z equal to square root R square plus XL minus X square. So how it will be? It's supposed to be minimum at, resonance,
XL
right?
equal
It's
to
supposed
X.
to be minimum at resonance. Agree? Yes?
Yes, sir.
Yes, sir.
Okay.
Yes,
So it
sir.
will be something like this. So if you draw a curve, so it will be something like this. So this is impedance Z. So this one is resistance. Whatever the circuit is having there, so that is its value. So that means this curve touches its minimum value at resistance. Understood? So at this point, so how the current look like? So how the current will be? So what is the current at frequency equal to 0? What is the current?
Infinite.
Infinity, sir.
Tell me again, what is the current if frequency is 0?
Sir, R.
Zero.
It's constant.
So, zero, sir.
Zero,
Right.
sir.
So why is 0? Because impedance is infinite, right?
Yeah.
Zero frequency, infinite, right? So it will start from 0. So it will start from 0, right? So when it will reach the maximum value,
Z equal to R.
that
Yes, sir.
resonant frequency, so it will reach the maximum value, right?
Yes.
So this will be its maximum value. So from that it will come down. So this is current value, peak value. So this is current. Understood? Clear? Right. In series resonance, so the impedance is minimum, so which is equal to resistance of the circuit, and the current is maximum. So what is current here? So I equal to V by R. In other words, V by R. Right. So that is the current. So resonant formula, so which is 1 by 2 pi square root LC, 1 by 2 pi square root LC. So omega r equal to 2 pi into FR, so which is the resonant frequency. So this resonant frequency or this resonance circuits, so especially we have applications in communication circuits. We have applications in communication circuits, especially where we require some bandwidth applications, or where we want to send some signals, right? So for these, so we require these resonant circuits. So we'll just try to solve one problem on this resonant circuit. So note down, a coil having inductance, inductance L, a coil having inductance L is connected in series with a variable capacitor. A coil having inductance L is connected in series with a variable capacitor. A coil L, right, is connected to a variable capacitor C. So the circuit possesses stray capacitance Cs. So circuit possesses stray capacitance Cs. Circuit possesses stray capacitance Cs, so which is assumed to be constant. The circuit possesses stray capacitance Cs, which is assumed to be constant and effectively in parallel with the variable capacitor. The circuit possesses stray capacitance Cs, which is assumed to be constant. So this is constant, right? And effectively in parallel with the variable capacitor C. So that means this is in parallel with C. Its value is Cs. Right. So when the capacitor is set to 1000 picofarad, so when the C set to 1000 picofarad, when the capacitor C set to 1000 picofarad, the resonant frequency FR is 92.5 kilohertz. Similarly, when capacitor C set to 500 picofarad,
We set to 1000 picofarad. What's it, sir?
92.5 kilohertz. The resonant frequency is 92.5 kilohertz. Okay. So when the capacitor set to 500 picofarad, the resonant frequency FR, so it is 127.8 kilohertz. So calculate stray capacitance Cs and inductance of the circuit. Right. So you may have doubt. So what is the stray capacitance? Right. So this generally stray capacitance, listen, or parasitic capacitance stray capacitance or parasitic capacitance. In general, in these electrical circuits, so this stray capacitance, which is usually occur, right? So this whatever we have, these electrical components are right. Usually they are put in one case, right? Or we'll put in some box kind of thing, right? So in these things, there is just a capacitance between the components, right? So there is just a capacitance between the components and the outer box. So those are known as stray capacitance. So these are known as stray capacitances. So for everything, for example, when you model a diode, for example, you have diode here, right? So if your diode is there, so this diode is having, so normally this diode is put in some case, right? So what is the outer one? So that is case. So with inside that you have some semiconductor material. So with that semiconductor material and the case, so you have some capacitance. So that is known as stray capacitance or parasitic capacitance. Okay. So usually when you model the diodes, so usually it will model with some stray capacitance. So we normally assume that the capacitance is in parallel with this diode, right? Even if you take the transformer is having some windings, right, inside that. So entire transformer is keep that in a metal box or a metal case, right? So with that metal case and the transformer windings, so there exists some capacitance. With that capacitance, there will be some leakage currents. So that that's a different story. So that things is known as stray capacitances or parasitic capacitance. Yes.
100 picofarads of CS.
Means this will damage the component, right? Because it is called parasitic.
No, it won't damage. Okay, its value is very small, right? And there will be some small leakage current will be flows. Okay, it won't damage. But if you want some high precision, especially in motor applications, if you want some high precision, so we need to counteract these capacitances. Okay. So how to solve this problem? How to solve this?
But we have to consider both the both the capacitors are parallel. So we have to take C plus CS in place of C.
You
And
have
we
to
have to
take,
take two cases for FR.
yeah, two cases, right? What is the first case? What is the
1 by
resonant frequency FR equal to 1 by 2 pi
1 by 2
square
pi
root
root of.
LC, right?
Yes, sir.
So what is C here?
C plus CS.
C plus CS, right? So first case, so we have 92.5 kilohertz, so which is equal to 1 by 2 pi. So what is this value? So L you have into C plus CS. How much it is? 1000 plus if you assume that this is also in picofarads, so CS into 10 to the power of what is pico minus 12. Pico is minus 12 only, right?
Yes, sir.
Okay. So this is second case, 127.8 kilohertz. So which is equal to 1 by 2 pi square root L into, so this is 500 only plus CS into 10 to the power of minus 12. So we can simply divide these two equations, right? We can divide these two equations, right? So will be 120, sorry, 92 point, if you divide these two, how much? So what you will get 92.5 divided by 127.8. So what it will be equal to? What is this value? Calculate.
Sir, 0.723.
Will it be like this? 500 plus CS by 1000 plus CS. Is this correct?
Yes, sir.
Yes, sir.
Okay. Right. So you just make a square of this one, right, and just solve it. So what is the value of CS?
56.
picofarad.
So 46.02.
85 picofarad, sir.
41.66.
So 46.
41.66.
Sir, 83.3, sir. 83.3
Just a minute, I
picofarad.
have answer for this. It is 50 picofarad.
Yes, sir. I got 50.42.
Okay. So it is 50 picofarad roughly. So you will get somewhere around 45.5. So divide by 0.909, something like this you will get. So it is 50 picofarad. Okay. Maybe somewhere you're not properly considered the points. Okay. So how to calculate the L value? How to
From equation.
calculate L value? Substitute in any expression, right? So substitute here or here any expression. So from that you can calculate the L value. So how much L you will get? What is the L value?
So 2.8 millihenry.
Yeah, 2.82 millihenry. So this is L. So do this. So note down one problem. So solve it at your home. So note down a series RLC circuit. A series RLC circuit. Otherwise, we'll put this one. Series RLC circuit having an inductance of 0.4 Henry. So this is 0.4 Henry. As instantaneous voltage as so inductance is having an instantaneous voltage of the circuit, so which is equal to 60 sine 4000 t minus pi by 6. Okay. And instantaneous current I, so which is 2.0 sine 4000 t. So this is I. Okay. So determine the value of R and C. Determine the value of R and C. Determine the value of R and C, and also at which the circuit will be in resonant, at which frequency the circuit is in resonance. We need to calculate RC and resonant frequency FR. Right? So I will provide the answers. So this is 26 ohm R. This is 154.8 nanofarad C, and the resonant frequency is H. So these are the answers. So instantaneous voltage is given, instantaneous current is given. So from that you need to calculate the L and R and C values, right? Or you need to calculate the C value first. After that you need to calculate the resonant frequency. So from that you can calculate the currents. Okay. Okay. So we'll move to the next thing in resonance phenomena. So why this resonance is important means, so this resonance is, so it will amplify the, first thing is it will amplify the voltage across the inductor and voltage across the capacitor, right? So how exactly, so that is amplified, so that we will discuss now, right? So before that you need to discuss one thing, so that is known as Q factor, or also known as quality factor. Q factor are also known as quality factor. So this is associated with energy storage elements. So this is associated with the energy storage elements L and C. Right. So thing is that, so in a resonant circuit, right? So in a resonant circuits, what will happen is, so there will be some cyclic interchanging of stored energy between the capacitor and inductor, right? So the resistance is, why the circuit is resistive only, because there will be some cyclic interchange between the energies between inductor and capacitor, right? So when the capacitor is fully charged, under this case the inductor is fully discharged, and vice versa, right? The energy is transferred to the capacitor and the energy is, again the same energy is used to charge the capacitor. So it will be something like this. So if you observe the voltage across inductor and voltage across the capacitor, so it will be something like this. So if we assume this is VL, so this will be VC. Thing is that the stored energy in the inductor is transferred to the capacitor, right? So once this capacitor is fully charged, again the stored energy in the capacitor is transferred back to the inductor. So this procedure is repeating. So this procedure is repeating. So that's why the circuit is only resistive. The circuit is only resistive. So now the thing is that in a resonant circuit, so this is the cyclic interchange of stored energy. So this is a cyclic interchange of stored energy, right? So but you have a component, so it will be like this. So this is not dissipating any energy. So this is also not dissipating any energy, but the energy is transferred between, so this and this. So that is the point, right? But so you have this resistance is there, right? But this resistance is dissipating the energy. but this resistance is dissipating the energy. Loss is in the form of current leakage. You will never get a pure inductive or pure capacitive elements. So these are associated with series resistance in case of inductance, a parallel resistance in case of capacitor. So these are associated, these are loss components. So if you are usually inductor is, how the inductor is made? So by winding, right, by making some turns in the winding, so we can make the inductance, right? So that means for inductor you require a wire. So for that wire you have some resistance. So this is the resistance of that one. Similarly for capacitor, so how this capacitor is required, how this capacitor is made? If you require two plates, electrolytic plates, so between those plates, so you may have some capacitance, right? So if their plates are there, so eventually there will be some leakage current in those plates. So that is represented as a high resistances, high magnitude resistances, right? So thing is that, so here if you consider the practical inductor or the practical capacitor, so even though in cyclic interchange, for example, the energy is changing between this component to this component. So in one half cycle, so it will charge this capacitor. In the next half cycle, it is charge this capacitor charge this inductor. So in between, so there will be some energy loss, right? So where this energy is lost? So this is due to the internal resistances and internal resistances of these two. So therefore, so how good this inductive element or how good this capacitive element, so that is decided by the this quality factor. So this is known as goodness of, so goodness of reactive element, are also known as figure of merit for a resonant device. The idea is simple, right? So for example, you have some energy is there, for example, 1000, right? So you have some energy of C. What is the energy that's stored in it will be? So that's of LIM square, right? So that is the maximum energy stored in the inductor. Similarly, the maximum energy stored in the capacitor is of C. What is the value? What is the maximum energy
Half
stored in
CV
the
square.
C
Half
VM
CV.
square, right? So the thing is that, so the energy transfer between, so this value to this value. So vice versa is supposed to happen at resonance, right? But it is having some internal loss. It is also having some internal loss, right? So but every cycle, so for every cycle, so there will be some associated with loss. So here also for every cycle, so there will be some associated loss, right? For example, you have one energy, one point is lost in every cycle. So obviously, if it's move on, right? So this energy will be reduced. So this energy is also reduced because of this internal power loss. So therefore, so we can define the quality factor Q, or how good that reactance, or how good that capacitor, how good that inductor. So that is 2 pi into maximum energy stored stored in that particular reactive element by energy loss per cycle. Energy loss per cycle. So this is the maximum energy stored. So that is, if in an inductor, it is half into L into Im square. So what is this energy loss per cycle? Right?
Half Li square minus half CV square.
So what is this energy loss? So this is due to the resistance, right? So this is due to the resistance of the particular inductor, right? Or particular resonant circuit. Agree? Right. So now this will be the, if you what is the energy loss? So what is power? What is energy? What is energy? Formula for energy.
I square R.
Power into time will gives you the energy, right? Agree?
Yes, sir.
Okay. So this is equal to average power dissipated into periodic time, right? Agree? Periodic time or the time required to complete one cycle. Agree for this?
Sir.
Right? So what is the periodic time? If it is a frequency, so this is time TR, right? Periodic time. So this time TR equal to 1 by how much it is? FR, frequency, right? Frequency of that resonant circuit or the the time period, right? Agree? So this can be written as Q, it can be written as, so this periodic time, right? So that is 2 pi into FR divided by maximum energy stored by average power dissipated. Agree? You have any confusion? You have any confusion?
No, sir.
No, right? So now,
No, sir.
so this is Q, right? So simple thing. So what is the maximum energy stored, right? And what is the energy or what is the power? So that is dissipated. So here, for example, for Q for inductors. So Q for inductance or Q for inductor for L, right? So what is Q? So it is 2 pi FR. So what is the maximum energy stored in inductor?
Half
Li
Li
square.
square.
Half
Of
Li square.
of Li square is the energy stored in inductor. What is the maximum energy stored in inductor? Half into L Im
L
square.
I max square.
I am square.
Okay.
Max
So
square.
divide
Yes, sir.
by, right. So what is the average power that is dissipated? We calculate the average power, right? What is that?
I square R.
I square R, right?
Yes.
So this Im can be written as, how to write this Im? Root 2 into, how to write this Im? Im is I by root 2, right?
Into I, sir. Root 2 into I, sir.
So root 2 into I, right? So write that. So what is this value and tell me?
Two pi FR into L by R, sir.
2 pi
FR
FR
into L by R.
L by R, right? So what is 2 pi FR?
Omega R, sir.
Omega R
R.
into L by R. So that is Q factor for inductor. Q factor for inductor. Similarly, Q factor for capacitor Q. So what is again 2 pi FR. So what is the maximum energy stored in capacitor?
Half C into omega
Half
C.
C square.
Half C
Into
Vm square,
V
right?
max.
By what is the power dissipation? Again I square into R. Okay. So now tell me, so what is Vm? How to write
Root
Vm in
2
terms of I?
I am at home.
Root to IR, sir. Root to IR.
Root to IR.
Yes, sir.
So this is Vm. How to write Vm in terms of I? What is Vm? If you know the current, what is Vm?
IM into
Sir,
R.
IM by C.
IM into R. Sir.
I see.
IM into R.
IM
What is Vm? Im into Xc. Is it correct?
Sir.
Agree?
Yes, sir.
Right. So what is Xc?
1 by omega C.
So that is Im by omega, right? Omega R into C. Agree?
Yes, sir.
Sir,
Okay. So why we are not considering the minus value? Because the Q is always positive only. Right. So now substitute. So what is Vm now? So what is Q now? So this Im can be written as I by, so root 2 into I. So what is this value? Q?
1 by omega CR.
1 by omega R into
C. CR.
CR. Okay. So this is the Q factor for a capacitor. Right. So these two are very important. This is a Q factor for inductor and this is a Q factor for capacitor. So one is omega R into L by R and another one is 1 by omega R into CR. So the thing is that this quality factor, so this is associated with the reactive elements. So it will basically gives the quality of the reactive power. So how much energy it is capable to hold, right? So with minimum loss, right? So with minimum loss.
Sir,
Yes.
R is the internal resistance of the reactive element, right?
Yeah.
Okay, good.
Not internal resistance, but yes, internal resistance only. Okay. Or the loss component in otherwise. So that is the loss component. This R is the loss component. So this loss component somewhere represent with the leakage and some may represent in series also. So that is depending on so how exactly they will do that. Okay. So somewhere represent with parallel thing, somewhere represent with this thing. The thing is that this R is the loss component here. Right. So we obtain two things. So one is omega R L by R, right? So R 1 by omega R C into R, right? So this omega R, so this is known as XL by R, agree? So this is XC by R. So in other words, Q, that is quality factor, so which is equal to reactance by resistance, reactance by resistance. Right. So if you multiply this one, so reactance, if you multiply with I square into XL by I square into R. So what is I square into XL? What is I square into XL and I square into R?
Average power of
What kind of power it is?
Reactive power.
Reactive
reactive
power.
Reactive power.
Reactive power divided by active power. Agree? So this is quality factor. So it is basically reactive power. We have already seen that what is reactive power in the definition. So this is a peak rate of energy stored in reactive elements. Okay. So don't be confused with this Q and this reactive power. Unfortunately, this reactive power is also represented with Q. Okay. Right. So quality factor, this is quality factor Q. So that is reactive power by active power. So in next class, we'll discuss the rest of the things. So any questions?
No, sir.
Okay.